This is section 10.4, the inverse circular functions. Alright, so before we get into the trigonometric inverses, let's first talk about inverses in general. First of all, a function has to be 1-to-1 to have an inverse. And what 1-to-1 means is that for each x, there is one y, which of course is the definition of being a function. And we can test that with the vertical line test. So this is the idea that it's a function to begin with. And we've got the vertical line test. To determine if that is indeed true. But the other part of 1-to-1 is the new part, perhaps for some of you, that for it to be 1-to-1 for each y, there is one x. And the way we can test that is with something called the horizontal line test. And if a function passes both of these tests, then it will have an inverse. And the notation for an inverse function, for the inverse of f, for example, is called f inverse of x. I want to talk about that notation for a second. When that -1 superscript is on the name of a function, like we've already used in this course, sine inverse of something, that means inverse function. However, when that same symbol is on a number, it has a different meaning. Like if I said 3 to the -1st power, that's the same thing as 1/3 to the 1st, which is 1/3. It means the multiplicative inverse, the reciprocal of. That's what that -1 means when it's on a number, or even when it's on something that stands for a number that you just don't happen to know. So we use that -1 superscript for two very different purposes, and you'll have to pay attention to what that -1 superscript is on. If it's on a number or on a variable that represents a number, then it's the reciprocal of. If it's on the name of a function like f or sine, that means it's the inverse of the function f or sine. Okay, so some other things that happen when you have a function f and its inverse, its inverse f inverse. To create the inverse function, once you've established that the function itself is 1-to-1 to begin with, and we're ready to find the inverse, the way that you do that is that you interchange the independent and dependent variables. In other words, interchange x and y. And when you do that, x things here become y things over there, and y things here become x things over there. So any ordered pair a, b on the function, you'll switch those, and that point will go to b, a. So every ordered pair on your graph, the x and y coordinates will switch for the inverse function. Some other things that happen is because everything that was x becomes y, the domain of f becomes the range of y. All x things become y things. And because all y things become x things, the range of the function becomes the domain of the inverse. Okay. And a side note about this switching of the ordered pairs is that if you graph a function, let me just graph one really fast here. Let me decide what I want to graph first, though. How about trying to think of one that's going to work really easily here. How about x cubed minus 1? So that's going to be our function. Y equals x cubed minus 1. And when we graph that, of course, when x is 0, y will be negative 1. When x is 1, y will be 0. When x is 2, that'll be 7, which is way up here someplace. Probably not to scale. I'm going to put a dot there, but that's probably not high enough. When x is negative 1, you'll get negative 2. When x is negative 2, you'll get negative 9, which is way down there. So this is what the graph of that function looks like. And I'm not actually going to go all the way up to that dot because it's not really specifically in the right spot. But that's pretty close to what that graph looks like. Now, if we were to graph its inverse, we would switch all ordered pairs. So 1, 0 would go to 0, 1. And 0, negative 1 would go to negative 1, 0. And negative 1, negative 2 would go to negative 2, negative 1. And the ordered pair 2, I believe that was 7, would go to 7, 2, which is out here someplace. Probably not in the right spot, but just so you kind of know where to go. And negative 2 was negative 9, so that would go to negative 9, which is way out here, negative 2. So somewhere out here, someplace, kind of where that n is in the word domain. And that function looks like this. Okay, and one of the things you might notice going on here is with the switching of x and y, it may become apparent to you if you look at it closely, and probably if you do several of these. If I were to graph the line y equals x, well, I can tell that I made a few errors in graphing that, but hopefully you can understand what I'm going to try to say. If that's y equals x, and the pink one is our function f of x, and by the way, is it 1 to 1? Is that pink graph 1 to 1? Does it pass the vertical line test? If you hold a vertical line anywhere, will it pass through there just once every time for each x? Is there one y? The horizontal line test is kind of the same. Hold a horizontal line anywhere on the y-axis, and for that y value, does it use 2 x's or just 1 for any given y? That's the horizontal line test, and it actually passes both. So this function is 1 to 1, and it does have an inverse function, therefore and we would label it f inverse of x. Now we're going to talk later about how to find, or pretty soon actually, how to find the equation for that inverse. And in fact, it involves interchanging the x's and y's. Let's go ahead and do that. Why not? So if we were going to find the inverse, we'll take the original equation that has x and y in it and switch. Every y will be written as an x, and every x will be written as a y. Then you need to solve for y. So add 1 to both sides, and then take the cube root of both sides to solve for y, and that is your inverse function, the cube root of x plus 1. That's the equation that we just graphed. Okay, now back to the line y equals x. If you had a better drawing, it would be clearer. I can tell that mine was a little bit off. But nevertheless, taking it for what it is, if you look at the graph of a function or its inverse, if you reflect the one you're looking at over the line y equals x, you'll get the other graph. So for every point on our original curve, it has a point on the other side of the y equals x line. Again, I said I didn't do a great job of drawing this. This actually right here isn't too bad. That point are on either side. And so this is the ordered pair generically AB. And this is the point on the inverse that's at BA. And whenever you do that, you get a reflection of the function over the line y equals x will be the graph of the inverse function. Okay? So that's kind of a neat thing about inverses. Now, there are plenty of functions that are not going to be one-to-one to start with. And so in order to find an inverse when it's not one-to-one, to begin with, if it's not one-to-one, find a domain restriction on F so it becomes one-to-one. Okay, so here are the rules for making a domain restriction. Okay, these are the rules we're going to follow. Number 1, maintain the range of the original function. That's very important. We don't want to lose any of the y values that the original function has. So that's a first rule, is you have to maintain that. 2, if the function is periodic, which this will impact us a lot in this unit because, of course, all of our trig functions are periodic. So number 2 is really important. With some of the algebraic ones, it wasn't an issue. So you may have never heard about this. We're going to choose a restriction on the domain as close to 0 as possible. Of course, you could go out to 100 pi, start there, but that's not actually going to be good. You want to stay as close to 0 as you can possibly get. Now, if you are as close to 0 as you can be for a periodic function, or a lot of other functions, this is also, number 3 is also important. But if you're given equally valid choices, where x is negative or positive, choose positive x values. And I'll show you an example of that in just a minute. Okay? So, those are important rules for restricting the domain, and we will have to do that because all of our functions all our trig functions will fail the horizontal line test. So, let's start with, I guess y equals sine of x is as good as any other to start with. So, let's do a graph of y equals sine of x. Notice this is just the vanilla, plain old sine of x, no transformations on the graph yet. Okay. So, y equals sine of x. So sine of 0 is 0, middle, then high, middle, low, middle, going this way, low, middle, high, middle. And that's a portion of our graph. And you can see, of course, I hope that this doesn't pass the horizontal line test. And one easy one to see that on is y equals 0. Is there only one x value that produces y equals 0? No, in fact, on this graph, it happens 5 different times. So this is definitely not one-to-one in its original form. So, of course, it does pass the vertical line test because it is a function. So I may forget to talk about that because all of our trig functions are functions, and they will pass the vertical line test part of the one-to-one requirement. Okay, so we're going to choose an interval that keeps our entire range. So we need to realize, well, what is that range? And of course, we go from a low of -1 to a high of 1. So could I, for example, go from pi over 2 to 3 pi over 2 and thereby keep all the y values from 1 all the way down to -1? Yes, that would work. Could I go from -3 pi over 2 to -pi over 2? Yes, that would work. So let me draw those in so you can see them. Could I use this restriction, and would that keep everything from -1 to 1? Yes. Could I go from here, to here, and keep all of the y values from -1 to 1? Yes. But those are not as close to 0 as you can get. And that's number 2, so we have to stay as close to 0 as possible. What if we started at -pi over 2 and went to pi over 2? Would that keep all of the y values from -1 to 1? Yes. And is that as close to 0 as we can get? Yes. Now, in this particular one, we have x values that are both positive and negative, which is fine because 0 is in the middle of it, and that's actually more important than trying to get positive x's. So if 0 is right in the middle of your domain restriction, that's great. That's probably the best one because that's as close to 0 as you can get. So the domain restriction we're going to make is we're going to keep only negative pi over 2 to pi over 2. And with that domain restriction, we'll be able to have an inverse for sine of x. So let's graph the inverse of sine of x. Now, one of the things you're going to notice is that everything that was x becomes y, and everything that's y becomes x. That means that although the x-axis for the function is numbered at every pi over 2, that's going to be our numbering scale for the y-axis when we're graphing the inverse. And the y-axis was marked off by 1s, which means the x-axis will be marked off by 1s. Do you see how we're switching? Everything that was x becomes y. Everything that was y becomes x. So our inverse function, let's take some ordered pairs like negative pi over 2, negative 1. That will go to negative 1, negative pi over 2. 0, 0 will go to 0, 0. Pi over 2, 1 will move to 1 pi over 2. And that graph looks like that. And if you reflected that over the line y equals x, you'd get the red graph over to the left. And so that is our inverse function. To find the inverse, we're going to interchange the x's and y's. So this will become x equals sine of y. Then we're going to do something called take the inverse sine of both sides. And we'll talk about this right-hand side a little bit more later. But we're going to, for right now, make the assumption that if you do sine inverse of sine of y, that's like, if they're truly inverses, you'll get back what you started with, y, and that will be what sine inverse of x will be y. And that will be the equation of our inverse function. Now this is a notation I prefer. It agrees with the calculator, but another good notation for inverse sine, you can call it arc sine, and it means exactly the same thing. Arc sine of x and inverse sine of x are the exact same thing, just a different notation. I like sine inverse because it's less writing, and sine inverse, as I already said, is on your calculator. So that one seems like a natural one to pick. Okay, so the inverse sine function means that y equals sine inverse of x, or y equals arc sine of x, means that x equals sine of y for all the y's from negative pi over 2 to pi over 2. Okay, so let's talk about the inverse graph for just a few minutes. What is its domain? Well, it goes from negative 1 to 1, which doesn't surprise me because that's what the range was for the original function. And every range thing, y thing, becomes an x thing, the domain. And what is the range of our function? Well, I just stated it, but I'll say it again. It goes from negative pi over 2 to pi over 2. Again, not a surprise, because that's the domain of the restricted y equals sine of x, the part we kept to make it 1 to 1. Okay, so got that down. Let's see if there's something else that we need to say. No, I think, well, a couple pages later there's going to be a kind of a summary for the inverse sine function. That's what I'm looking at. This is an increasing function on its domain. This inverse is. And the x-intercept and the y-intercept are both 0, and its graph is symmetric with respect to the origin. So because of its symmetry with respect to the origin, it means it's an odd function. And what we know about that is that if you take the function and put negative x into it, you'll get back the opposite of your original function. So this is an identity for an odd function, even odd function, and this is the inverse of sine is odd, just like the regular trig function of sine of x is an odd function. Okay, so let's go about doing a few problems with this. So using what we just learned, that if I gave you y equals arc sine of 1/2, what that means, and this is what we're going to do whenever we have an inverse trig function or an arc trig function, we're going to start by rewriting that using the definition of the inverse function. And so think about what that means. It's saying that the sine of some angle y is 1/2. That's what y equals arc sine of 1/2 means. So that the sine of that angle y is 1/2. So the question, when you're asked for an arc sine or an inverse sine value, I want you to keep in mind that that is an angle. The arc sine of 1/2 or the inverse sine of 1/2, you're getting an angle answer. Okay? And we're going to be using radians. You can see this is in radians. This is in radians. So we're in radians. Okay? So think about what angle would give you 1/2 if you took the sine of it. Now there's something really important I need to say before we get too far into this, is that any answer we get for inverse sine or arc sine, whichever way you're going to call it, if I have a circle of possibilities, the angles going from 0 to 2 pi, what angles of those are valid answers to arc sine? Well, if you look at the range, it's anything from negative pi over 2, including negative pi over 2, to pi over 2, including pi over 2. So whenever you're doing inverse sine, the answer you get has to be an angle between negative pi over 2 and pi over 2 inclusive. So what you might think when you're doing a problem like this is, okay, I know that sine of y being 1/2 is in those two quadrants. The only possibility for that is in the first quadrant when this is 1 and that's 2, right? Because we couldn't use the second quadrant version of that, which would normally have been something we considered, because there y is 1 and r is 2. But it's not an acceptable answer for arc sine. It has to be an angle between negative pi over 2 and pi over 2. Now, it's not between negative pi over 2 and 0 because that's where y is negative, and our arc sine is of a positive number. So what is that angle that I just marked inside of that triangle that would give us the angle between negative pi over 2 and pi over 2? Well, hopefully you're able to say, well, that is when y is pi over 6. And so that's what the arc sine of 1/2 is. It's pi over 6. Okay? Let's do another one. Y equals sine inverse of -1. And of course, what that equation means is that we would take the sine of an angle to get an answer of -1. And that's actually one of the special answers we get for a quadrantal. When is the sine of y equal to -1? It's right there. Remember on the quadrantals, we use a unit circle, and so the sine is the y-coordinate of the point when that happens, and that's the only place on the unit circle where y is -1. And what angle is that? And I know you're tempted to say 3 pi over 2, but that's not an acceptable answer for sine inverse. The answer is actually it's -pi over 2. So you have to train yourself to think I can only have answers between -pi over 2 and pi over 2 for any of these inverse sine questions. Okay, so let's do this one. Y equals sine inverse of -2, which would mean that the sine of y would be -2. Well, that's plainly not possible. If I look at the graph I just used, there is no point on that circle where y is -2. It just doesn't exist. So this sine inverse of -2 does not exist. There's no value for it. Another reason I can say that is, if you'll recall, our domain for sine inverse, so for y equals sine inverse of x, its domain is -1 to 1, and -2 is not in our domain, which means it doesn't have an inverse sine value. Okay, so be careful that you know the ranges and domains, because if the input for sine inverse is not in the domain, -1 to 1, the answer won't exist. And then for the angle you're getting, it has to be in the range from -pi over 2 to pi over 2. So lots of stuff to keep track of here. Okay. Okay, let's move to cosine. Y equals cosine of x. So let's graph the original function. Okay, sine of 0 is 0. Oh, thanks. Cosine of 0 is 1. Oops, can't see that. That's okay. So then, I'm trying to color code this to be the same. Oh yeah, use pink. Okay. So cosine of 0 is 1. Then we get middle, low, middle, high, middle, low, middle, high. This function, of course, is not 1 to 1 because it fails the horizontal line test miserably. And so we're going to have to restrict the domain using those 3 rules. So we're going to keep the entire range. So the first thing I do is make sure I know what that range is that I'm keeping. It's -1 to 1. And now we have to make a decision about our domain restriction. So if I wanted to keep -1 to 1, could I keep like from pi to 2 pi? Yep, that would work. How about from -2 pi to -pi? Yep, that would work. Is there anything closer to 0 than those 2 options? Yes, there is. From -pi to 0, or from 0 to pi. So the purple and orange one are equally good choices. They're the same distance from 0. They include 0 and then 2 marks to the right or 2 marks to the left. So they're equally good as far as that's concerned. One isn't closer to 0 than the other. So this is that first time we're going to see this. Given equally good choices where for one of them, the purple one, x is negative, or for the orange one, x is positive, we're going to choose the positive x values. And so that means that our domain restriction that we're going to choose goes from 0 to pi, inclusive. Okay, so let's graph the inverse. So as we did last time, we'll number the x-axis by 1s because all the x and y stuff switches when you do the inverse. And we'll make our marks on the y-axis every pi over 2. Right, so doing a switch of some ordered pairs, 0, 1 will go to 1, 0. Pi over 2, 0 will go to 0 pi over 2. And pi negative 1 will go to negative 1 pi. And that is the graph of our inverse cosine function. Which of course can also be called arc cosine of x. For the arc notation, you just put the letters ARC in front of the regular 3-letter abbreviation of the trig function. If you want to use that notation, you certainly can. I use the inverse, but you can use the other one if you want. Okay, so what is its domain? Well, it's going from negative 1 to 1. No surprise, that was the range of the original function. And what is its range? It goes from a low value of 0 to a high value of pi. Again, no surprise because that's the restricted domain we chose for cosine. Okay, this is a decreasing function on its domain. Excuse me. The x-intercept is 1. The y-intercept is pi over 2. Let's see, was there anything else we talked about? Let me look up at the other one. Increasing intercepts domain range. Oh, does this one have any kind of special symmetry? It's not symmetric with respect to the y-axis, and it's not symmetric with respect to the origin. So this one has no special symmetry, which means it has no even-odd identity, because it's neither one. So there is no even-odd identity for inverse cosine, which is strange because we've had an identity for every trig function, but we're not going to have an even-odd identity for the inverse trig function, cosine inverse. So that's kind of interesting and something to take note of. Okay, so I drew a little picture, and I like my picture that I draw for this. If you have cosine inverse, if you have cosine inverse, and we're allowing for the thought that it could be any angle from 0 to 2 pi, the range of inverse cosine only gives you answers of 0 to pi. Any answer for inverse cosine will be an angle between 0 and pi if there is indeed an answer for the question. Okay? And so I'm going to draw these little pictures like this to remind you of what is a valid answer for what's inverse cosine of something. Okay, so let's do our first example of that. Y equals arc cosine of 1. And that equation means if you take the cosine of some angle y, you're going to get an answer of 1. What is that? Well, 1 is one of our special answers from the circles that are ones that have it's a quadrantal angle is what I've been meaning to say. And when it's a quadrantal angle answer, like 1 or -1 or 0 are undefined for sine or cosine, then that's when we use the unit circle. And cosine gives you the x-coordinate of the point, and the only place where the point has an x-coordinate of 1 is at the angle 0. Right? That's 0. And I have to pick a number that's between 0 and pi inclusive, so that's why I chose for it to be 0, because the cosine of 0 is 1. Okay, let's do another one. Y equals cosine inverse of negative square root of 2 over 2. Okay, once you try this one, pause the recording and come back in a few minutes and see how you did. All right, let's see how you did. Keeping in mind that I can only use first or second quadrant angles, and that what that equation means is that the cosine of some unknown angle y is negative square root of 2 over 2. I might recall, and hopefully you will too, that that comes from simplifying -1 over square root of 2. And that's what we would normally think of as x over r. So I want to draw a right triangle in standard position. Well, the angle will be in standard position such that x is -1 and r is square root of 2. Whoops. Make it a little bit bigger. So let's say it's -1. Then the triangle is this one. And the reference angle for the 1 square root of 2 triangle, the reference angle is pi over 4. And so the angle in the second quadrant that's represented here is 3 pi over 4. And so y equals, getting some lagging, sorry. Let's see if I can, okay. Y equals 3 pi over 4. So the inverse cosine of negative square root of 2 over 2 is 3 pi over 4. Okay. All right, so let's move on to the inverse tangent function. So graphing the normal tangent function is our first task. And you may remember that the tangent is undefined at odd multiples of pi over 2, which means it has vertical asymptotes when x is equal to an odd multiple of pi over 2. And it's an increasing function, which means it goes from -1 at 1/4 of the way between the asymptotes, to 0 halfway through between the asymptotes, to 1 at 3/4 of the way through the asymptotes. And then you repeat. -1, 0, 1, draw the curve. -1, 0, 1, draw the curve. Okay, so that's what tangent of x looks like. So what I'd like for you to do is see if you can come up with the information I used when I was working with sine and cosine. See if you can get all that information by yourself. So pause the recording and come back and see how you did, if you got it all right. All right, so let's see how you did. The first thing you need to think about is that you want to retain the entire range of the original function, because this is of course not one-to-one, but fails the horizontal line test. So what is the range of tangent? Well, it's -infinity to infinity, all real numbers. And so to keep that, we could have just one of those curves by itself. So we could do the one on the far right, the one on the far left, the one in the middle. Which of those is closest to 0? Well, hopefully you saw that the one that uses 0 right in the middle of it is the closest you can possibly get to 0. So this is the part of the domain we're going to keep. And it goes from -π/2 not inclusive, because there's a vertical asymptote there, to π/2. That's the domain restriction we're going to have. So when we go to get the inverse tangent, or arctangent, of x, because of the switching of x's and y's, we'll number the x-axis by 1s and the y-axis by π/2. Oh, wait. Make that a little bit bigger. π/2. Okay, so let's switch some ordered pairs to get that inverse. -π/4, -1. I'm sorry, yeah, -π/4, -1 will go to -1, -π/4. 0, 0 will go to 0, 0. π/4, 1 will go to 1 π/4. The vertical asymptote at x equals -π/2, when we're switching x's and y's, will become an asymptote at y equals -π/2. And so any vertical asymptote, when you do the inverse, becomes a horizontal asymptote. And of course the equation of that is y equals -π/2, if anyone asks. And then, of course, the one that's at x equals π/2 will be an asymptote, horizontal asymptote, at y equals π/2. And again, if someone asks, you ought to be able to find the equations of these horizontal asymptotes. And then the curve approaches that asymptote. So we're going to go like this. And that's what the arctangent of x graph looks like, the tangent inverse of x graph. So what is its domain? All reals. No surprise, that was the range of the original function. What is its range? Well, on the low end, you're bounded by negative pi over 2 without actually ever reaching it, and you're bounded above by pi over 2, again without actually ever reaching it. Okay. This is an increasing function. The x-intercept is 0, which is also the y-intercept. The little picture I'm going to draw for this is that of all of the angles 0 to 2 pi, the only ones we can use are the ones from negative pi over 2, not including it, to pi over 2, not including it. So this looks a whole lot like the sine graph for this same purpose. You just can't include anything that came from a vertical asymptote. So I can't include negative pi over 2, nor can I include pi over 2. But still, that means that any angle we're going to get from arctangent is going to be a first quadrant angle, nice small acute positive number, or it's going to be in the fourth quadrant with a negative very close to 0 number. It will not be between 3 pi over 2 and 2 pi. Although it's in the fourth quadrant, it will be between negative pi over 2 and 0. So that's something to pay attention to. Let's see if there's anything I forgot to say. Oh, it is symmetric with respect to the origin. So it is an odd function, which means it has an even-odd identity. So tangent inverse of the opposite of x is the opposite of tangent inverse of x. Okay, and that's about it for that one. Okay, so for the other three, I'd like to actually I want to do all of them. Sometimes I do and sometimes I don't, and I think this is well worth it, so that you understand. So let's go ahead and keep going. I'm going to speed up a bit because it's the same story very many times in a row. So let's next do y equals cosecant of x. Okay, one on the y-axis. And if you'll recall, this one has asymptotes at x equals 0, x equals pi, so multiples of pi is what these are, 2 pi, which I didn't draw a 2 pi mark, so I'm going to draw one, or pretend like I drew one, pretend like it's about right there, negative pi, x equals negative pi, and x equals negative 2 pi. Again, I failed to draw one over there. Okay, and so if you'll recall this graph, halfway between the y-axis and the first asymptote to the right, it has a high value. For sine, the guiding function has a high value of 1, so its reciprocal is 1. So 1/6 of the way, the answer is 2. 5/6 of the way, the answer is 2 again. And we get the upward pointing branch. Sine of x at 3 pi over 2 has a low of -1. Its reciprocal is -1. So 1/6 of the way we get -2. 5/6 of the way we get -2. Goes like that. And repeat. Okay, so this is a graph we've seen before, so I'm going to just graph it rather quickly. Obviously this one is not one-to-one, does not pass the horizontal line test, and so we have to restrict the domain. And our first task in doing so is to make sure that we keep the entire range. So the range is from -infinity to -1, including -1, union, starting up again at 1 and including 1, and going to infinity. As it turns out, the part of this we're going to keep is from -pi/2 to 0, which gives us half of a downward branch, which will get us everything from -infinity up to -1. And we'll use the asymptote at 0, and then we'll pick up right after 0 and get all the values from 0 to pi/2. Okay, so the domain restriction we're utilizing is -pi/2 to 0, not including it because there is a vertical asymptote there, union 0 to pi/2. Okay, so when we go to graph the cosecant inverse, or arc cosecant, cosecant inverse, or arc cosecant of x. The x-axis will be numbered by 1s, the y-axis numbered by pi/2, okay, so the vertical asymptote at x equals 0 will be a horizontal asymptote at y equals 0. The ordered pair -pi/2, -1 will go to -1, -pi/2. And then the curve will just approach the asymptote like that. And then the point that's at pi/2, 1 will go to 1 pi/2. And then the graph will approach the asymptote like that. So of course that means that the domain of this function is the x values we're using are from -infinity to -1, union 1 to infinity. No big surprise, that's the range of the original function. The range of this function is from -pi/2 on the low end up to 0 but never getting there, union starting after 0 and going to pi over 2, which of course is our restricted domain from earlier. Let's see. So this function actually decreases on its domain. Let me think. What else do I want to say? It has no intercepts. It is an odd function, which means it has an odd identity. So cosecant inverse of negative x is negative cosecant inverse of x. Let's see, what might I have forgotten? Oh, it does have a horizontal asymptote at y equals 0. I think I mentioned that earlier, but I'm not sure I said the equation of the horizontal asymptote. Let's see, anything else? Okay, so that's that. Oh, I know what I haven't drawn yet is the picture that I've been drawing with each one of these is of a circle, and what part of that circle we're using of all angles possible from 0 to 2 pi. What are we using here? So we're using from negative pi over 2 to 0, not including 0, so open circle, and then from 0 not included to pi over 2. So before I go any further, I'd like to mention that there are 3 of them so far that have basically been from negative pi over 2 to pi over 2 with maybe a point or 2 left out. And I'd like to summarize those together and kind of point out how they all go basically. Their range is negative pi over 2 to pi over 2. Again, we're leaving out places where there are asymptotes. The ones that do that are inverse sine of x, its reciprocal function, reciprocal of sine, that is. So cosecant inverse has basically the same restriction, and the last one, tangent inverse. And the reason I think of that one going with these is if you think of the quotient identity for tangent as sine over cosine, it's dominated by sine because sine is in the numerator position. So sine, its reciprocal cosecant, and the ratio of 2 functions that's dominated by sine, tangent, all 3 of those share this basic same restriction on the range of the inverses is basically negative pi over 2 to pi over 2 with a point or 2 points left out, as you've seen already. So cosecant inverse leaves out 0, and tangent inverse leaves out negative pi over 2 and pi over 2, and sine inverse uses everything. So I wanted you to see how those kind of go together. All right, so let's move on to secant inverse. So we're going to start with the secant graph, which is not 1-to-1. So we're going to have to restrict its domain. So all of this is very similar to what we thought of before. And again, every time I'm doing this, and it's like the second or third time through, you might find it useful to pause and see if you can do this correctly by yourself first, and then listen and see if you were able to capture everything that's needed. You may capture some, you may capture all, but at least give it a try. Okay, so this one has vertical asymptotes at odd multiples of pi over 2. We know that its guiding function cosine has a value of 1 at 0, so this will have a 1 as a low point, 1/6 of the way 2, 5/6 of the way 2, draw the upward pointing branch. At pi, it has the low value of -1, the guiding function does, so 1/6 of the way -2, 5/6 of the way -2. Goes like that. And then over here, it's a repetition, as we've seen before. So we'll just draw that in. All right. Okay, so what domain restriction do we want to keep on this thing? Well, we want to keep the entire range. And so the range that we want to keep is from -infinity to -1, union 1 to infinity. That's what we have to keep. And we got to make it 1 to 1, so it passes the horizontal line test. So you have two choices. You could go from 0 to pi, or from -pi to 0. Either one of those would work. The better choice is, because you can use positive x's, is to go from 0 to pi over 2. Use that asymptote and go from pi over 2 to pi. Okay, and so the domain restriction there is 0 to pi over 2, union pi over 2 to pi. Okay, so that should look familiar. And in fact, I'm going to go ahead and draw the restriction circle that I've been drawing for this. The range that we'll get for arc secant or secant inverse will be from 0, including 0, to pi over 2, not including pi over 2, then from pi over 2 to pi, including pi. Now, does that sound familiar, where we're leaving out the middle point? Yeah, that's just like what happens with cosecant inverse. So there are some things that you can see that are patterned, and it's like, oh, we're leaving out the middle value. We did that with cosecant as well. So let's graph the graph for arc secant. Arc secant of x, which is also known, of course, as secant inverse. That's what I actually wrote first. Okay, so the x-axis will be marked off by 1s. The y-axis will be marked off by pi over 2. The vertical asymptote at x equals pi over 2 will become a horizontal asymptote at y equals pi over 2. So there's a horizontal asymptote at y equals pi over 2. So the point 0, 1 will go to 1, 0, and then the curve will approach the asymptote. And there will be there's a point at pi negative 1, so its inverse point will be at negative 1 pi, and the curve will approach the asymptote. And so, of course, you can see that the domain of this function is you start at negative infinity, go up to x equals negative 1, stop, and then pick up again at 1 and go to infinity. And the range, you can see, is on the low end 0, goes up toward pi over 2 without reaching it, union, and then pick up at pi over 2 without using pi over 2 itself, and going from there up to pi, and using pi, includes pi. Okay, so this is an increasing function. It is not symmetric with respect to the y-axis nor with respect to the origin, so it has no special symmetry, which means since it's neither even nor odd, it will not have an even or odd identity associated with it. See, the x-intercept is 1. There is no y-intercept. Let's see if there's anything else that I need to talk about. Already mentioned y equals pi over 2 is a horizontal asymptote. Okay, I think that's everything I wanted to say. There might be something I left out and it might pop up later, but I think I covered everything. Okay, let's do the last one, cotangent, and its inverse. Okay. So, doing like we always do for a non-transformed graph, we use marks on the x-axis of pi over 2 and marks on the y-axis of size 1. Cotangent has vertical asymptotes at 0 and pi and 2 pi and negative pi, so multiples of pi. It's a decreasing function. And so, starting at the y-axis, it starts out at the 1/4 of the way with positive 1, halfway 0, 3/4 of the way negative 1. Draw the curve. Repeat. 1/4 of the way 1, 0, 3/4 of the way negative 1. So it repeats itself. Okay. Remember, we're going to try to stay as closest to 0 as we can, so I'm going to not even draw the last one on the far left. You have two good choices. You could go from 0 to pi to keep the entire range, which of course is negative infinity to positive infinity. So we could go from 0 to pi or from negative pi to 0. And of course, given two equally good choices, where one has positive x's and the other one has negative x's, we choose the one with positive x's. So we're going to choose this one, which means that our domain restriction we're making is we're going to start at 0 and not include it because of the vertical asymptote, and go to pi and not include it because of the vertical asymptote. Okay, so now if we go to graph its inverse, which means we'll be graphing y equals cotangent inverse of x, also known as, there we go, arc cotangent of x. We number off the x-axis by 1s, the y-axis multiples of pi over 2, the vertical asymptote at x equals 0 will become a horizontal asymptote y equals 0. The vertical asymptote at x equals pi will become a horizontal asymptote at y equals pi. So those are our horizontal asymptotes, y equals 0 and y equals pi. Then, using some points at pi over 4, we have 1, so 1 will graph pi over 4. We have a point at pi over 2, 0, which will be graphed as 0 pi over 2 for the inverse. And then the point at 3 pi over 4, negative 1, will be at negative 1, 3 pi over 4. And then we'll have a curve that looks like that. Its domain is all reals, which is what the range of the function was, so no surprise. And its range is from 0 to pi, including neither one. And again, that's no surprise, because that's the domain restriction we made on the original function. This is a decreasing function. It's not, doesn't have any special symmetry. It's not symmetric with respect to the y-axis, nor to the origin. So it does not have an even-odd identity. It has no x-intercept. The y-intercept is pi over 2. Let's see if there's anything I forgot. Nope, I think that's it. All right, so then drawing the circle that I've been drawing over and over again. Oh, oops. Let me try that again. Well, that was not a whole lot better, but I'm just going to leave it alone. Okay, for this one we're going from 0 to pi, but we're not including 0. And we're not including pi. That should remind you of the tangent inverse. We didn't use the endpoints for that one either. And so, again, that helps if you kind of find patterns and see similarities and dissimilarities, and make sure that you understand those so that you don't confuse things. So basically we're going to use from 0 to pi with maybe some omissions, like this one omits 0 and pi. secant inverse omitted the middle point, pi over 2, and cosine used all of it, 0 to pi. So these three, cosine, its inverse, the reciprocal of cosine is secant, and the inverse secant uses basically 0 to pi, again with the middle point left out. And this one, I think a cotangent is dominated by sine because it's cosine over sine. So the inverse cotangent has the same basic restriction, 0 to pi, that cosine inverse and secant inverse also have. But of course, cotangent inverse doesn't use the first nor the last point going from 0 to pi. So hopefully that gets all of those firmly in your head, and so that you can use those. If you look at the notes a little bit further on, you'll see a summary of each function, its domain, its interval, that is its range, and what quadrants it uses. That's actually captured in the pictures that I've been drawing, like from 0 to pi, don't include 0, don't include pi, and the quadrants for that one are 1 and 2. So my little pictures are summaries of what they have in a table. Almost always, inverse trig functions are defined with real number values. That means we're in radians, not degrees. Most of the time. Sometimes we will want degree measured angles, and we'll just have to convert what we know the exact angle to be. Like pi over 6, we'll have to convert that to 30 degrees if the context requires a degree measured angle. Now, some issues with calculator. If you look at your calculator, you're going to find a button for sine inverse of something, for cosine inverse of something, and for tangent inverse of something. The other three inverses do not have a button that you can get at all on your calculator. You just can't. So what we're going to have to do is, if someone says, what's sine inverse of 0.2? Well, since that's a button on the calculator, make sure you're in radian mode and type sine inverse. So I'm doing that right now. Sine inverse, second sine is what mine has me do, of 0.2. And I get approximately 0.201. Since they didn't tell me how many decimal places I'm rounding to, since I made up this problem, 3 numbers after the decimal point is good. Or if I ask you, what's cosine inverse of negative 0.9? Well, you just type that in your calculator. Second cosine, negative 0.9. And I got 2.691 using 3 decimal places. Let's see, tangent inverse of, oh, I don't know. Let's do negative 3.1 and see what we get. Tangent inverse of negative 3.1 is negative 1.259. Okay, so those are no big deal. You just type them in. If I give you a problem like any of these 3 on the left, type them in, make sure you're in radian mode, and record the answer. Boom, done. For the other 3, it's not so easy. So let's say that we had to find what is y equal to cosecant inverse of, say, 103.5 or something. What we're going to have to do is first rewrite that without the inverse. And this is a skill you need to develop. This equation is the same thing as saying the cosecant of some unknown number y, some angle y, gives me an answer of 103.5. Make sure that you can convert an inverse equation into an equivalent non-inverse equation. Then, knowing that we only have sine and cosine and tangent on the calculator, I'm going to rewrite that as cosecant is the same thing as 1 over sine of y. Then I'm going to take the reciprocal of both sides of that equation. And then go back to an inverse now that it's sine of y, and y will be sine inverse of 1 over 103.5. So notice that for the sine inverse, it's not the reciprocal of sine inverse, it's sine inverse of the reciprocal of the number. And that's very easy to mess up, and of course if you type it incorrectly, it's going to give you an error anyway. So anyway, if you're doing a problem like this, I would expect you to write all of that down, because that's the work that says why you're allowed to type what I have. Okay, so now type that in your calculator. So sine inverse of 1 divided by 103.5, that's about 0.010. Okay, so I'd like for you to try this one. Y equals secant inverse of negative 8.34. And when you're done with that, I'd like for you to try y equals cotangent inverse of 2.8, and then y equals cotangent inverse of negative 12.8. Okay? So try those, put this on pause, try them, and see how well you do. All right, so let's see how you did with these. So since secant inverse is not a button on the calculator, I would suggest you rewrite this without the secant inverse, without the inverse, as secant of y equals negative 8.34. Take the reciprocal of both sides. Now that it's in terms of a button that is on the calculator, cosine, rewrite it in terms of an inverse, and that's cosine inverse of negative 8.34. And now it's ready to type in. So second cosine is a cosine inverse of 1 divided by negative 8.34. And you should get about 1.691. Okay, let's do the next one. So this equation is the same thing as saying that the cotangent of unknown y is 2.8. Oh, and probably what I should have said, let's go back for just a second. For all of these, the range of sine inverse, what was that? It was negative pi over 2 to pi over 2, right? Is 0.201 between negative pi over 2 and pi over 2? Yeah, pi over 2 is 1.57. Yeah, it's definitely between, so that's good. Cosine inverse, its range is from 0 to pi, is 2.691, somewhere between 0 and pi, which is 3.14. Yeah, it is. Tangent inverse, its range is negative pi over 2 to pi over 2, is negative 1.259 between negative 1.57 and 1.57? Yes, it is. The range of cosecant inverse is negative pi over 2 to pi over 2, not including 0, is 0.010 between negative pi over 2 and pi over 2? Yes. Okay, secant inverse, its range is from 0 to pi, not including pi over 2, is 1.691 between 0 and pi? Yes. So the calculator knows what it's doing, and if you're worried about it, you do need to realize that it's a good machine, and it'll usually do exactly what you tell it to do. So I'm going to take this equation and take the reciprocal of both sides, and I actually perceive a problem right here. Let's see if you can think it through with me and see why I see this as a problem. And then writing this without, with the inverse would be y equals tangent inverse of 1 over 2.8. Okay, so looking at the original, well, let's just type that in first, sorry. Tangent inverse, so second tangent of 1 divided by 2.8. I got about 0.343. Keep in mind, the original function of this problem was cotangent inverse. And cotangent inverse has a range of 0 to pi, right? From 0 to pi, not including either one. You can't be 0, can't be pi. Is 0.343 a number between 0 and pi? Yes. So, yay, that one's good. You may be wondering why I'm stressing this on this one especially. Well, if you think about cotangent inverse, and it's 0 to pi, basically. But in the calculator, we're using tangent inverse. And tangent inverse only goes from negative pi over 2 to pi over 2. And if the answer for cotangent inverse has to be between 0 and pi, but tangent inverse might be between negative pi over 2 and pi, I see a contradiction. Now, if it's first quadrant, no problem. You'll get the right answer. The question is, if it's cotangent inverse, we're supposed to get a second quadrant answer. Let's see what we get over here. So writing this equation, without the, I'll go ahead and leave that in a different color, kind of highlight it. Rewriting the equation without the inverse is cotangent of y equals negative 12.8. The reciprocal on both sides would be tangent of y equals 1 over negative 12.8. And so what you might type in your calculator is tangent inverse of 1 over negative 12.8. We type that in, second tangent of 1 divided by negative 12.8, and I get an answer of negative 0.078. Now, the original problem here was cotangent inverse, and it only gives us answers between 0 and pi, right? Well, here's the problem. If you're taking the cotangent inverse of a negative number, you're not going to get back the correct answer. That's kind of sad. But it's fixable, because what you're going to get is, for tangent inverse, you're going to get some fourth quadrant negative angle answer. Let's say it's here. And if we drew that in and made a right triangle out of it, the good news is that the correct answer over here has an angle, a reference angle, that's the same size as the reference angle that we get. So that's the good news. Those two reference angles are the same. The one that we're getting from the tangent inverse of a negative number, that's negative 0.078, is on the right track. It's just in the wrong quadrant. And one thing you might remember from geometry is that if you have what are called vertical angles, they're always congruent. So if you have two lines that intersect at a point, the vertical angles will be congruent. Well, if we're drawing this and this angle is congruent to that angle, that implies that this x-axis and this ray and that ray have to be lines, which means that this ray here and this ray here are part of the same line, and it's giving us the answer in the fourth quadrant, but we're wanting the equivalent answer in the second quadrant for it. All we have to do to get from this negative answer that we have to the answer that's between 0 and pi is to add pi, add half of a rotation. So what we're going to have to do when it's cotangent inverse of a negative, this one's weird, so you're going to have to remember it, it's different. You're going to go through the same process, but if it's a negative 12.8, a negative argument for cotangent inverse, and it's the only one you have to do this on, you're going to have to add pi before you're done. So I hope that negative 0.078 number is still in the calculator, and just hit plus pi and get what is the correct answer for this, 3.064. And that is a number that's between 0 and pi, because pi is 3.1415, whatever, right? Okay, so that's the weird one, cotangent inverse of a negative. If you're doing this in the calculator, you have to put it in your calculator and then add pi to get the correct answer. Okay. All right, so to summarize, the calculator part of this, to do cosecant inverse of a number, what you do is you do the sine inverse of the reciprocal of the number. So go back and look at the example we did and see if that statement isn't true. If we want to do secant inverse of something in the calculator, we're going to have to type cosine inverse of the reciprocal of that number. And if we want to do cotangent inverse of x, there are two possibilities. This is the weird one, and you're going to have to remember this is strange. You're going to type tangent inverse of the reciprocal of your number whenever x is positive. For negative x's, you are going to take tangent inverse of the reciprocal still, but then you have to remember to add pi to get the right answer when x is negative. Does that make sense? All right, so let's do some problems where you're going to be using this. So I'd like for you to try all of these on your own and see how you do. So find y when y is cotangent inverse of -5. Find y when y is arcsecant of 7. And C, find y when y is cosecant inverse of -1.05. Okay, pause your recording and try those. Okay, so for the first one, because it's cotangent inverse, and it's cotangent inverse of a negative number, the way to get this answer is to do tangent inverse of the reciprocal of that negative number, and then because it's negative, add pi. And so if you type that in your calculator, you should get 2.944. Okay, for the next one, for arcsecant, what we'll type in our calculator is cosine inverse of the reciprocal of 7, 1/7, and typing that in the calculator, you should get 1.427. And then for the last one, you'll find y by taking sine inverse of the reciprocal of the argument, and you should get -1.261. All right. Now, the next set of problems, we're getting away from the calculator, so put your calculator down, and we're going to do these. These ask us for exact values, and anytime that's happening, basically you shouldn't be picking up your calculator. Okay, so y equals cotangent inverse of -1. Y equals arcsecant of 2. And y equals cosecant inverse of 2 square roots of 3/3. All right, so this means that the cotangent of my unknown angle, y, has a value of -1. I haven't said this yet, but I kind of don't like using y for these inverse trig function values. And right now it's about to rear its ugly head at me and say, no, I really don't want to do that. So let me go back and I'm going to change these problems. You will have to be able to deal with it if it's called y, but I'm intentionally going to call it something else because of an issue that we're going to encounter. So instead of using y there, I'm going to call it, since it's an angle I'm getting, I'm intentionally going to call that theta, and theta, and theta. And I probably should have done this earlier to kind of to underscore the fact, highlight the fact that what we're getting is an angle answer. And I forgot to change this one. So let me go in and get rid of that. And, oops. There we go. Call that theta now. So, and this is what I was thinking. Because the definition of cotangent of an angle is, in terms of x, y, and r, is x over y. And you see now this is y, because this y and the y of the original problem are not the same y. It's a totally different idea. And so that's why I would rather you call it theta so as not to confuse yourself. Because if you're going to use the definition and talk about like x over y or y over r over y or whatever, you want that y to have the correct meaning, the trig meaning that we've been using it for. Now, to get -1, I'm going to have to divide 1 and -1, and I don't know which of those x or y is the negative. So to guide me in that, I'm going to think about cotangent is ruled by cosine, right? Cosine over sine, so it's ruled by cosine. And I remember that cosine is basically, cosine inverse is basically 0 to pi, which means this is basically what cotangent is. So if you look at everything I just shaded in green, which letter, x or y, is always positive? Right, it's y. So what that means is that if it's negative number, it has to be the x that's making it negative, not the y. So within the green region, I want something, some triangle where x is -1 and y is +1. And that's the 1, 1 square root of 2. So 45, 45, 90 right triangle. And in this quadrant, if the reference angle is pi over 4, I know you were thinking 45 degrees, because so did I. What is that angle? That angle is 3 pi over 4. Okay, does that make sense, what we're doing there? So that's what the value of cotangent inverse of -1 is. It's 3 pi over 4. All right, so writing the b, why don't you pause and see if you can do the other two by yourself. Now that we've done that one together, see if you can do the others by yourself. Okay, maybe you're back now. So rewriting this without the arc part of the problem, without the inverse, that means that the secant of this unknown angle theta is an answer of 2. And I remember that secant is r over x. So I'm going to need to put that over 1 so that I have a fraction. And then I'm going to think about the circle. Secant, like cosine, as we just saw, is basically 0 to pi. So I want r to be positive. Of course, it's always positive, but I want x to be positive. So I want x to be a +1 when r is 2. And that's the 1, 2 square root of 3 triangle. And the reference angle there is pi over 3. And because we're looking at a positive answer, we know it's in the first quadrant there. So it is pi over 3. And so arcsecant of 2 is pi over 3, which we temporarily called theta. Like that. Okay. Okay, then the last one. Writing that without the inverse, that would become cosecant of theta equals 2 square roots of 3 over 3. I might want to remember where that came from. That came from rationalizing 2 over the square root of 3. Okay, so cosecant is r over y. Then cosecant, which is closely related to sine, has the same restriction as sine does. It's from -pi over 2 to pi over 2. So we're looking for a triangle where r is 2 and y is positive square root of 3. So that's square root of 3 and that's 2. Oh, that's the same triangle we just used in the previous problem. So we know the reference angle is pi over 3. And that is actually the answer we want, because we want something that's either in the first quadrant or in the fourth quadrant between negative pi over 2 and pi over 2. And that fits the bill. So theta, which was cosecant inverse of 2 square root of 3 over 3, is equal to pi over 3. Also, just like problem B was. All right. Let's end this one and go to a part 2 video. I think we've got enough on 1. So stop this recording, go to the next one.